Hello, my name is Derek Johnson, and today I'm going to walk you through the entire process of getting DeepSeek running using ONNX Runtime on your Snapdragon X Elite compute platform. More specifically, you will be running on Qualcomm Hexagon NPU. Roll up your sleeves, let's get started. As always, let's get started by ensuring that we are within the correct Python environment. We need to be using a Python environment that is compatible with Windows on Snapdragon. If you need more detailed instructions regarding environment setup or setting up your Snapdragon X Elite in general, I encourage you to go over to the blog that is associated with this video, as we'll go into more details. So as we see here, we are using a Python version that is compatible with Windows on Snapdragon, and we're ready to go. If you do see AMD 64, that lets you know that you're on an emulated version of Python, and you will not be able to use Hexagon, our NPU, if you're on an emulated version. You need to be in a pure Python version that's compatible with Windows on Snapdragon. Now we'll go ahead and handle all of our imports. These imports, all of these are supported natively on Windows on Snapdragon version of Python. So we don't have any issues that we kind of ran into with HRNet and OpenCV before. This will be smooth. So what we have is ONNX Runtime. We'll import our OS, NumPy, and then some pathlib. And then, of course, we'll also need a tokenizer to be able to ingest the tokenizer that's provided by the models and use that when we're encoding and decoding our string sequences. We'll use pathlib just for plumbing, which we're going to take care of now. Okay, so we'll first start by establishing our root directory. For me, it's going to be this users DFS QNN sample apps. This will get the root directory. When you pip install our repo, this will point to exactly where you need to be at. Next, we're going to identify the path to our ONNX Runtime. Why we're doing this is because when you pip install ONNX Runtime QNN, you also get all of the drivers that are necessary to run on Hexagon. We need this path so that we can point to that driver. So as you see here, I have my virtual environment set up, and this is going to go to the ONNX Runtime within that virtual environment. And this will lead us to where all of the different drivers are at. So the driver for Hexagon, the driver for CPU, etc. Now we're going to initialize all of the different ONNX files that we'll need in order to get DeepSeek running on our NPU. So this is going to be, so how I have the file structure is I have all of the models in a subdirectory called QNN DeepSeek R1 Distill Quinn 7B. This model will have a model that will handle the embeddings. We'll have another model that will initialize our context. We'll have another model that we'll use once we get into our autoregressive loop. And then we have a head model that will return our logits from what both context models output. And then, of course, we need to point to where our tokenizer is at as well, which is also within that subdirectory, the QNN, the model subdirectory, which we call it now. Now that we have all of the different graphs identified and all of the tokenizer and basically all of the file names that we need, let's go ahead and complete the plumbing by establishing these paths. So here we have the model path, which is going to be in our root directory, models, and then our model subdirectory. Our initial context path, our context iteration path, our head path, the path to our tokenizer, and then here you see we're going to use this ONNX root path in this subdirectory CAPI, and then this is going to be the driver that we also have access to. So what does this look like? And we can see now we have the full path. Now that we've completed all of our plumbing, let's go ahead and set up all of our inference sessions. We will have a separate inference session for each one of these graphs. Let's walk through this really quick. So here, the first thing right here, we're just going to set up our session options. And I'll do this because sometimes I do want to get profiling from ONNX Runtime. Right now, we're not passing anything to session options, but just in case you want to. Another important piece is setting up your QNN provider options. So here, the backend path, of course, we have to point to Hexagon. And then we have this HTTP performance mode. And as I said previously, if you want more information regarding this, either go to the blog or you can go to the docs here. But essentially, this lets the Hexagon know what performance mode we want to run at. So for example, burst is basically saying we want Hexagon to run at the highest frequency possible. It's going to max out everything. You can also do a low power mode, which will extend it even more than what we already get, the battery life. So putting my electrical engineering hat on, what burst is we're going to run our NPU at its highest frequency. To achieve this highest frequency, we have to apply a higher voltage. So a higher voltage means we're going to consume more power. So burst is the fastest guy we have. If you want to look at some other options and play with other options, I encourage you to go to this site or go to the blog where all of the options are listed out. Then we have this SoC model. If you go to the Qualcomm SDK site, you can find what SoC model corresponds to whatever platform you're using. Because we are on Snapdragon X Elite, I know the SoC model is 60. We also have something that's very convenient in profiling level. So I just selected detailing. What this will do is this will output to this directory a file that gives you all the details about what's going on in graph creation, everything that Hexagon is doing to build this graph in the backend. You'll get those details. And then finally, we have this HTTP graph finalization optimization mode. I have this 3. I believe this is the highest level, but of course you can go here again to this execution providers QNN to get more details on the different optimization modes. Basically, the more optimization you want, the longer, very minuscule, but the longer it may take for the model to initialize, but you'll have a more optimal graph, which in best cases, it leads to faster computation. So now that we've set up all of our QNN provider options, and there's more of these. As I said, if you go to this site right here, we'll go ahead and set up our sessions. So each session, I have the variable name, which is going to determine what this session does. So we first have our embedding session. What is the embedding session? This is going to take our inputs, our tokens, and run it through our embedding layer. We're going to pass our providers, which is going to be, we're going to pass the model path, which we've already determined in the plumbing. And then we're going to pass these QNN provider options. So it gives it, hey, we want to run this at burst. We could actually play with this and have different provider options for different sessions. So say we know that when we run the initial query through the embedding layer, we don't really need a high performance for this. So maybe we set this to low power and we extend the battery life even more than what it already is. But for our case, I just pass the same QNN provider options to every single session. And then session options, if you want to let ONNX Runtime do some profiling or look at all the other options that ONNX Runtime has, you can pass that as session options. So this is just going to be our embedding layer. This is going to be our context iteration session that when we go into our autoregressive loop, and we'll discuss more of this as we go, as we continue, we'll use this guy. Then we have this context session, which we'll pass our initial query through, and then our head session, which we'll use to grab the logits from each one of these context sessions. We'll run this. And so if you see this error, all you need to do is restart your kernel. We're aware of this issue and we're actively working on it. So when we restart our kernel, and let's just say run all. Okay, so now we see we're cooking. So now we see that we do have access to our QNN execution provider. We also have CPU execution provider. If you're only seeing CPU execution provider, then you need to go back and check the path that you have going to either the driver, or come back up here and make sure that you're using a Python version that's compatible with Windows on Snapdragon. We're seeing QNN execution provider. We know we have access to Hexagon. we're ready to continue. As always, now let's inspect what the different sessions, inference sessions, what the models expect as an input and what it's going to give us as an output. If you looked at the HRNet blog or you looked at the HRNet video, you know I like to use Netron. We're going to skip that for now. So we have our embedding inputs. And we see that the embedding layer is expecting an input shape of 1 by the sequence length. So basically batch size 1, our sequence length, int64, this is pretty self-explanatory. And for the output, it's going to give us an output shape of 1 by the sequence length by this 3584. So remember I said the purpose of this embedding session is to take our inputs, run it through the embedding layer, and then give us the output. So what this is telling us is that for each one of our tokens that we pass to this layer, now we have the embedding dimension or the vector dimension for each one of these words. So if you just to quickly recap, each word is going to be associated with a vector of 3,584 columns. You see that we have, if you remember what the embedding layer does, is it's basically the embedding matrix is essentially a lookup table. When we pass our input tokens to the embedding layer, it's going to return those words, those tokens, as well as their vector dimension, which is going to be a vector dimension size of 3,584. And then the type is going to be a float. And then the name of this is going to be the input to our hidden states. So now we'll do the same thing and expect our context session. So what's the expected input to our context session? Now it gets interesting because we have the output of our embedding session, which is going to encode each tokens with their vector embedding. But the input to this context session is going to be a 1 by 4 by max sequence length by 128. So we'll kind of just remember these numbers and we'll get into what this means later. And for the outputs, now we're going to get a 1 by 64 by 3,584. So what this kind of alludes to, if you remember back to what the output of our embedding, where we had 1 by sequence length by 3,584, this is saying that, okay, we're getting something with our vector embedding dimension, but we have 64 here, which we'll talk about that later as well. But this kind of just gives you some context. So we're starting to see some connections between these different layers. Although the input, in an ideal world, you think that the output of this one would match the input of this context session, which it doesn't. But the output of our context session does kind of look familiar with the output of our embedding session. We have 64 tokens that each have a vector embedding dimension of 3,584. Now let's inspect the context iteration session. For inputs, now our context iteration session, now we're looking at a batch size of 1, a sequence length of 1, and then of course I think we're all familiar by this time that this is our vector embedding dimension. So why do we only have a 1 here? So this initial context session, we have 64, but for this iteration, we only have 1. And this is why I say we use this one when we go into our autoregressive loop, because if you remember autoregression, we're only predicting 1 token at a time. So we'll get into that when we get into our autoregressive loop. And now for the outputs of this context iteration, it's the same. So that's this one's going to be easy to deal with. So we input a 1 by 1 by 3,584, and our output is going to be 1 by 1 by 3,584. And last but not least, let's look at what the head session expects. as an input and what it's going to give us as an output. So now what the head session expects almost matches the output, or it does match the output, thankfully, of what we're going to get from the different context layers. So for this context layer, we're getting a 1 by 64 by 3,584. For this context layer, we're going to get a 1 by 1 by 3,584. So this context layer can process multiple tokens at once. So 64, as a reminder, is going to be 64 tokens, each having a vector embedding of size 3,584. This is going to be one token having a vector embedding dimension of 3,584. The input to the head session is going to be a sequence length, or however many tokens we want to pass to it, a vector embedding size 3,584. And the input is going to be the hidden states of the context sessions. So for context, this guy, where the name is going to be, we're going to output the hidden states. For context iteration, we're going to output the hidden states. The hidden states are going to be the input to this layer. And what do we expect as an output to this head session? From this head session? Logits. Finally, something we can do something with. So what we're going to get is the logits. The output shape is going to be 1 by the sequence length by this large number, 152,064. So what does this represent? This is going to be our entire vocab size. So every single word that is comprised in that embedding matrix, we're going to get a logit for each one of those words. So the sequence length is going to be either 1, it's going to be 64, it's going to be whatever it's going to be. And we're going to get the entire vocab size. We're going to get a logit for every single word in that vocab size. So that's what this is going to tell us. Okay, so at this point, we've ensured that we were in the correct environment. We've done all of our imports. We've handled all of our plumbing. And now we see that we've instantiated our inference sessions, and now we've inspected our different model graphs. Now we're into the next section, initialization. Now that we've got all of the plumbing, we've got all of the imports, the paths, and we inspected our models, let's start tokenizing. The first thing that we need to do is load the tokenizer. We were provided this tokenizer JSON, which maps all of the different characters, the different string sequences to its particular token ID. So that's what we're going to do here. We're going to fire this up and basically load in this JSON file, which is going to be parsed by this tokenizer module. And then we're going to we'll get access to everything. It makes it easier. So now that we have our tokenizer loaded up, let's go with our first query. For this query, in keeping with the theme and keeping up with the theme of why you should be running your LLMs locally, let's just ask the large language model why it feels that we should be running our AI models locally. So this is going to be the query. Imagine you are a cybersecurity professional. Provide step-by-step reasons why AI models should be ran locally. Please consider all aspects of data privacy and cybersecurity. For DeepSeek, so these are going to be special tokens that DeepSeek is trained on. This think just prompts it to go into its reasoning. And then we're going to go ahead and tokenize. So we'll take this initial query. We're going to encode it, which is going to return the token IDs. So let's run that. And now we're going to inspect the different token IDs. After we encode our initial query, what are the token IDs that will correspond to each one of these different strings? Well, here we have it. We'll have one special character that's automatically added to the encoding. This is going to tell the LLM that we're starting our beginning of sentence. This is going to be our user, And then for each character in here, depending on how to, now some tokenizers will break up, maybe it'll break up here and say these are two different tokens. But either way, every single word in this string will correspond to a different token size, to a different token. And this is what's ultimately going to get fed into the LLM. So we've inspected our token IDs. Let us now take these token IDs and we need to turn it into a NumPy array, because this is what's going to get fed into our embedding session. And each one, well, we'll get to that when we get to the embedding session. So what's the shape of this? So the shape is going to be, for each token, it's going to be, we have basically the size of this array right here. So we have 38 tokens, batch size of 1, 38 tokens. At this point, we're ready to run these tokens through our embedding session. So we have 38 tokens that we're going to run through the embedding session. And then we'll get, what we'll return is each token, each one of these token IDs will have a vector embedding dimension of 3,584 associated with it. So what the embedding output returns is going to be the batch size, 1. Let's just say the amount of words in our query. So the amount of initial words in our query, and then the vector embedding associated with each word. And that's going to be of size, this size. So the embedding dimension. So that's it for our embedding session. We did our first action that we need to do before we can get to the inference part. So before we get any further into our initializations, let's take a step back to kind of get a deeper understanding of this model. So of course we're gonna use these parameters throughout, which is why it makes sense to define them now. Batch size, of course, that's going to be 1. So our sequence length is going to be the initial sequence length of the tokens that we initially passed. So basically the 38 here, or if we had another initial query, whatever the size of that, that's what's going to be this sequence length. Now the hidden size is going to be the dimensionality of each token embedding vector. So each one of these 38 tokens will be associated with a vector the size of 3,584. For this model, we have 28 attention heads for each transformer layer. The size of each transformer head is going to be 128. So it should be our embedding size, our dimensionality of each token embedding vector divided by the number of heads will give you the attention head size. In this model, we also have 28 transformer layers. So what did we just say? We have 28 transformer layers. Each layer has 28 separate attention heads, which attend to 128 different pieces of the matrix. And then we have this max sequence length, and this is only for our initial pass. This isn't the global context window of the model, as we'll see when we do the inference. We will return way more than 64 tokens. But for our initial pass, our initial query, the model is designed as such that we limit the max number of the initial query. So what's the initial query? It's going to be this. So you cannot have more than 64 tokens in this initial query. We're safe right now because all of this was only 38 tokens. And then we have another thing that we have to keep in mind. We have this number of key value heads. Traditionally, in full multi-head attention, each one of these attention heads will have its own query, key, and value. This model is using what's called grouped query attention. So what that says is that each attention head will have its query, because that's what we'll use to pass our initial tokens to, but they're going to share key and values. So if we have 4, then we know that if we have 28 attention heads, we divide this by 4, then that means that 7 attention heads will share a key value head. That was a lot, But that's essentially the model structure that we're dealing with right now. And we'll keep using these variables as we go. So if you didn't quite catch that, it'll show up again. Temperature, we'll get to that later. So now we have a high level understanding of the structure of our model. Let's initialize our key value cache. So that's what we're going to do here. We're going to start with an empty key, KV cache. It's going to be a dictionary. And this is what the model expects. If you're interested in how it all looks, I encourage you to go over to Netron and inspect it there. And you will see how the model is using these pass keys, pass values, so on and so forth. But essentially what we're going to do here is we're going to iterate through the number of layers. These are transformer layers. We have 28 of them. And the pass shape is going to be batch size, the number of key value heads, the max sequence length, and the attention head size. If you remember, this is the input to our context layer as well. So if I just scroll up, this is what we're saying right here. So this is going to be the input. It's going to be 1 by 4 by max sequence length by 128. But now we know that this corresponds to the number of key value heads, the current max sequence length, and the amount that each attention head attends to at a time. So that's what we have here, attention head size. And then we're just initializing, MP zeros. We're going to initialize it with zeros for the empty KV cache. And we're also going to initialize the pass values. The length of this should be 56 because we have 28 layers and we have a key and value for each layer. Okay, so now we have the empty KV cache initialized. Let's go ahead and initialize our sequence length. So we're just going to use the shape. So basically 38, we know that the output embedding shape is going to be 1 by 38 by 3,586, 3,584. And we're just going to use the tokens. So, and then we have to subtract 1 because remember we're doing zero-based indexing because of Python. I'm going to say that I want the data type to be int32 and then reshape this. And then our maximum sequence length is going to be this 64. So, and remember, this isn't the max context window of the model in itself. And then data type int32. This is pretty self-explanatory. Just again, to sum it up, this is our initial sequence length, which is based on the size of our initial query. And this is going to be the max sequence length that we can pass to that first layer. So now let's just put these into a dictionary. And the reason I'm putting these into a dictionary is because this is what our context layer, our initial context layer, this is the structure that it's going to expect. So we'll have these, I'm just going to call this dictionary sequence lengths. We're going to have a key pass sequence length, and we're going to pass this initial sequence length to that key. And then total sequence length is going to be our max sequence length. We're going to pass that to this key, and that's what we get. So we have our initial query and then 64, which is going to be our max. Okay, so we're in good shape now, but we have to take care of something, because if we go back up to what our model expects and what it outputs, there's a mismatch. So remember, we went from our embedding session where we had an input of our sequence length, which is basically just going to be the amount of tokens in our initial query. We got an output of this sequence length, but it expects a max sequence length, which is 64. But here, the output that we got, if you remember, is going to be 1 by 38 by 3,584, which is going to be here. But we need to get up to our max sequence length of 64 in order to pass it to our initial context layer. Our context session. So what we have to do is we'll need to pad these. So basically go from 38 tokens, and we need to bring it up to the 64 tokens that our context layer expects. How we do this is by padding, by using padding. And there's a special, if you look inside of that token.json file that we imported, which you can look at it, you can find the padding ID. So for this particular, the tokenizer that this LLM uses, the number is this 151643. So now essentially what we're going to do is we're going to say, after you're done with our tokens that from our initial query, we're going to add this 151643 to everything else to bring it up to a shape of 64. So how we do this is initially, first I'm going to say, okay, I want the batch size, the sequence length, and the embedding. So this is going to be our initial batch size. So if we go here, just to bring it back to our memory, we have 1 by 38, our initial query, by the vector embeddings that's associated with each one of those token IDs. So now we're going to create a full vector embedding of a full matrix of shape, batch size 1, max sequence length, embedding dimension. So what this gives us is this will give us a matrix of size, batch size 64 by this embedding dimension 3584, and it's going to fill this matrix with this padding ID of 151643, and then we're going to make sure that the data type is consistent with our output embedding. Now what we're going to do is we're just going to say, okay, from this padding embedding, I want you to give me everything from batch size. For this part, which is going to be here, I only want you to use up to the sequence length. So from 0 to the sequence length, we're going to have the actual tokens. And then I want you to keep all of the vector embeddings as well. And when we do this, what this is going to do is essentially mask our embedding output. So after this sequence length, after this 38, it's going to have this padded ID of 15163643. And now we see that with our padding, we went from embedding output shape of 1 by 38 by 3584 to 1 by 64 by 3584. Again, essentially, we're just creating a mask. This is going to be a full rank mask of 1 by 64 by 3584. And we only want to keep the token embeddings. We want the actual token embeddings from 0 to the sequence length. Everything else we want to keep 151643. That's what this is. And just because I don't necessarily believe anything until I see it, I want to ensure that this padding actually took place. So what we see here, this is going to be all of our vector embeddings. So each one of these vectors are going to be of size 3584, and they're going to correspond with our initial tokens. But if we do 1 plus the sequence length, we should see our padding ID, which is here, 151643, right there. So now we know that after our last actual token from our initial query, we're padding everything from there on. We can also do one more thing. Start here and go to the end. And everything after our sequence length is going to be 15163, which is our padding ID. And the model is already trained to know that basically this is nothing. Or we should get a token right here. I always just check a million different ways because I want to ensure that what I'm doing is actually what I expect it to do. Okay, so now we've initialized our KV cache. We've set up our sequence lengths. So our initial sequence, our max sequence, and we padded our initial query, our initial token IDs. Let's put it all together. What we're doing now is we're going to create another dictionary, and we're just going to put all of these different things that we've already, so this empty KV cache, this dictionary sequence lengths, And then we're going to add these input hidden states. The input hidden states will be what we just created. So this will be 1 by 64 by 3,584. So one thing to keep in mind also is that if we just look at our pass key 0, which we've initialized, this is the shape. Remember, this is the shape that is expected by our initial context layer. So we have batch size 1, number of KV cache heads, our token size, and then our attention head size. Okay, so now we finished all of our initializations. We set up our initial KV cache. We understood that there were some slight nuances with what our context model expects in what comes out of our embedding model. But now we're all cleaned up and we're ready to go. So let's go ahead and pass this initial prompt input with all of this into our context session. So now we see that we get the output of this model is going to be after running through this first context session, is going to be 1 by our max sequence lengths by our vector embedding for each of those tokens. And let's also quickly inspect what the prompt output actually gives us. Here we go. And this is going to comprise the KV cache, our sequence lengths, our hidden states, everything. It's a lot. And upon further inspection, so what is our initial prompt output? As you can see, we have a huge array of, and this is going to comprise our KV cache, our token length, our hidden states, everything. But we can break this down and inspect it even further. And upon doing so, let's just look at the first index from these prompts. And what we get is our hidden states. So these are the hidden states that will be used for the next session, which will be our head session where we actually get the logis. And what we get is that we have the batch by the prompt length up to max 64 tokens, and then of course our embedding size. And of course, I just keep reiterating this. Each token has a vector embedding of this size. So that makes sense. This is our output hidden states. Okay, so for the prompt outputs, what comes out of our context session, the first index will always be the output of our hidden states. And this is going to be of batch size 1, our sequence length, our prompt length, and then the vector embedding size. Every other index after that, and we'll just look at 1 for now, is going to give our KV cache information. So what we see is we have a batch size, the number of key value heads, the sequence length, and the head dimension, so our attention head dimension. And this is going to be for every single layer. Okay, so now that we see that our index 0 is going to be our hidden states, and every index after that is going to correspond to our KV cache. Let's go ahead and update our KV cache from this prompt. So that's what we're going to do here. Remember, 0 index is our hidden state, so we don't want to populate anything there. So we'll start at the first index, and then we'll just run through the number of layers and update the KV cache with the values that come out of our context session. And we'll do the same thing for the values. So we have 1 for the keys, we update 1 for the values, and then what we'll get is something like this. So pass key 0 will be this guy, and then so on and so forth. Pass key 1, and if we just take here, dot keys, we'll see that we have a key and a value for every single layer, every single transformer layer, to be clear. Now that we've got our hidden states from the output, and we have our key value updates for the next prediction, and we've also updated our KV cache, now we'll pass those hidden states to our head session. So what this head session is going to do is it's going to take those hidden states from the context layer, run it through another layer that's going to return our logis. If you notice, we're not doing anything with our KV cache here. All we're doing strictly here is getting our logis. And if you remember, so now we have this. And if you remember what our logit size shape is going to be, it's going to be 1 by 64 by our entire vocabulary size. So every single word that we're able to have a token for, we're going to get, a logit for every single word. So after we run through our head session, we're only going to add our hidden states to the head session. It's going to run it through this graph, and what we're going to get is our logits. Now, if we look at the shape of the logits, what is this telling us? This is telling us that for each token, we'll have a vector of every single word that we have in our vocabulary, every single word that the LLM has a token for, we'll get the logits that will essentially tell us the probabilities, so on and so forth. So 64 tokens, each one of these tokens has a logit that comprises the entire vocabulary that the LLM understands, or the entire vocabulary that the LLM knows that there's a token ID for. So now that we have all of these logits, we have for every single token, we have this complete word vocabulary associated with it. But really, for prediction, we only care about the last logit. So that's going to be this guy. And if we look at the shape of this one, we see that it's basically the last token, and then every single, of course, like we said, the entire vocabulary size is going to have a logit attached to it. So what do we do now? We're going to start with a greedy sampling technique. And basically what we're going to say is, I want you to look through this entire array, give me the max logit, or the max, which is going to correspond to the token ID with the highest value. So np-argmax, look at the last logit, the last token. Yeah, not the last logit. Give me the last token, look through the entire array, and give me the index that holds the max value. So the max one of these numbers, I want the index of that. 65004. And this is going to be our next token ID. This is what the model is going to predict and use to begin our autoregressive loop. And if we want to know what this token ID corresponds to, it corresponds to a where. So we basically just said tokenizer, decode this token ID, and tell me what string is associated with it, what word is associated with it. Okay, so now at this point, we've updated our KV cache, we got our initial hidden states, we use those initial hidden states to make a prediction for the next word. When we got the prediction, we initially got a shape that included every single word in the vocabulary and had this entire word dictionary, I'm just going to call it dictionary, this entire dictionary of words that we're able to use. But we only care about the last word. So the last word is going to be, the last token is going to be here. And then we say, hey, just give me the max logit. This is what we call greedy sampling. We're not doing anything with probabilities. We're just saying the max value from this array of 152,064, just return that index. And that's what we got, decoded it, and it was aware. Okay, so now we've used our initial context session. We've input our initial query. We've tokenized that query. We've initialized our KV cache. We ran it through our embedding session. We ran the embedding session. We post-processed that, padded some of the tokens that we needed. We ran it through our context layer. We got our initial KV cache, and we got our logits from our hidden state. Now the next thing to do is we'll use that KV cache. We'll use our next token prediction, which we know is 65004, and we'll begin our autoregressive loop. So autoregressive loop, and you can look this up, so I'm not going to go too deep, but basically we're going to take the entire generated sequence and we're just going to keep on adding. We're just going to keep predicting the next word. So let's just start with the max token of 50. And what this is going to say is I want this thing to predict a max of 50 tokens. Our generated IDs is going to start with our token ID right here. And then our previous sequence length, remember we padded this to 64. So we're just going to use that same previous sequence length. So now we'll enter our autoregressive loop. And this will be relatively quick because everything that we're going to do here, we've already discussed previously. So we're going to enter our loop, the max number of tokens, which we've just established here. And then what we're going to do initially is we're going to create a NumPy array from our next token ID here, add this to input IDs. Now here, because I like to see what it's saying, I'm just going to print these, I'm just going to decode this as it goes. So as we iterate. And then we're going to run our input IDs through our embedding session. So we've done that before. We already understand what that does. But remember, for this guy, it's only going to be one word. And we're going to run that through the embedding output. Next, what we're going to do is we're going to create our lengths dictionary with our past sequence length. And this is going to be this previous sequence length and then the total sequence length. So now you have to remember that we're adding 1 to the sequence. So it's going to be the previous sequence length plus 1. Now we're going to create our iter inputs from our previous KV cache, our present KV cache, which came out of our initial context layer, our new input hidden state, which came from our predicted token, and then our new lengths. So we have to update this, and we're going to send this to the next session, which is going to be our context iter session. So remember that even though this was our next predicted token, our present KV cache is going to hold all of the context of our previous, it's going to hold all of the context of our initial query. And then these lengths, we just update that. And then we'll just pass this to our context iter session, which you remember, it's only going to expect a 1 by 1 by 3,584 because we're only going to pass one token, and we're going to also pass all of the key value from the previous, from our initial query. We're going to pass that as well, and then these lengths. So from here, we're going to grab we're going to grab the hidden states from this, and then we also need to update our KV cache because now we have a new token, we have a new key KV cache, so we need to update that, and we'll use that autoregressively when we do our next prediction. So this is the part where we're going to update, and we've seen this previously. We already discussed this. No need to go deep into it. So we're updating this KV cache, and if you think about it, we update it here, and when we go to the next loop, it'll be used as the inputs for our next prediction. We'll grab our logits, and because we're using a greedy scheme, we'll just go ahead and barrel through the rest of this. We'll grab the logits. Remember, we only want the last token. We only want to use the last token. We say, hey, out of the entire word size, what's the max? Give me the index of the max logit. Where does that reside? We'll use that as the next token ID. We'll append that to our generated ID. So now our sequence is getting longer. And then we need to update our previous sequence length. So, and then of course, this goes back through the loop. So now our previous sequence length is going to be updated here. That's going to be the past sequence length. We're adding another one. We're using our KV cache that we updated from here. And it's just going to keep going through this loop. And then just to keep track of what we got, let's go ahead and we'll pass. So once we've gone through our max tokens, we're still using a greedy sampling scheme. Let's see what we get. And mind you, keep in mind, this is all running locally on our NPU, as you can see here. So we only asked for a max of 50 tokens. Our initial query was, imagine you're a cybersecurity professional, provide step-by-step, and we can let it go longer. Let's see how deep it goes. Let's just go to 1,000. Let's see what kind of answer it gives us. And because I don't want it to use the same KV information that it did previously. So I'm going to start here. and just run all of this again, because I wanted to start from a fresh KV cache. And it's already making a good case for why you should be running. You see all the controversy regarding, who's hosting these LLMs, what they're doing with the data. One of the first things it says is, my data isn't sent to someone else's servers. That's the big plus for wanting to run your LLMs locally. Keeps everything private. Your data is your data. It's asking. So now it's going through the reasoning. If the app is created by a third party, it's asking questions, asking itself questions. We are still cooking on this NPU. Now, this is kind of the whole controversy with DeepSeek, where they're saying, it's running on somebody's service and other servers, and we don't necessarily know what's going on the servers. Well, here we're running it locally. So we don't have to worry about anything because all of our data is staying here. The other benefit is if the servers go down, we don't have to worry about that because I could not have any Wi-Fi. I could turn the Wi-Fi off, and because it's local, it doesn't matter. So while we're waiting for this to finish, let's go ahead and make this more efficient. We're using a greedy sampling technique, which in most cases isn't ideal. We're actually getting a pretty decent output here, but in most cases it's not ideal. So we're going to introduce a few concepts. Temperature, we're going to introduce top K, and then we're also going to implement a repetition penalty. So the first thing we're going to implement is this repetition penalty. Remember, we need to get our last logit, and we're just going to pass this through this repetition penalty. If the generated sequence, if it sees the same token more than once, we're going to throw a penalty on it. Next, let's implement our temperature. So we have the temp. I think the temp is defined somewhere up there. Just in case it isn't, let's just put a temperature of 0.8. I think that's what the DeepSeek paper recommended. And then it's going to intake the logits, and it's going to return probabilities. Now, lastly, we're going to implement our top K. And for top K, it's going to take in the probabilities. I want to do top K of, let's just say 50. So the 50 tokens with the highest probability. The 50 tokens with the highest probability. And then we're going to return these token indices and the token in the top probability, or the top indices and the top probabilities. And the last thing we're going to do is we're going to replace this greedy sampling technique with this guy. And it's basically going to take in the top indices, the top probabilities, and just randomly pick a choice for our next token. Add that to the sequence, and we'll continue on. Let's see what we get now for a response. And I created the softmax using this just for easy, so you can easily read it, but because I like one-liners. Let's also implement the same function using a one-liner. Now, let's run this. Okay, so here we have it. The LLM is done. We're up and running in this Jupyter Notebook. And here from the LLM itself, why you should be running locally. 1, data security. 2, computational power efficiency. 3, dependency chains. Security risk mitigation, so you don't have to worry. Regulatory compliance. Privacy protection, which is the big one. Control and accountability. Potential counter arguments. And then it just gives some counter arguments. While cloud-based solutions offer advantages, localized AI provides essential capabilities needed for replicating real-time functionalities and managing interpretability. Benefits of localization. Features like enhanced interpretability are achievable in-house through replicating similar capabilities. Cloud-wise requires substantial investment. And then customer trust, which is another big one. Local operation can enhance user confidence in AI systems functioning where they are based, fostering greater trust and satisfaction. So that concludes this entire walkthrough. We went from implementing just having models to running a full LLM within Jupyter Notebook using Snapdragon X Elite and Hexagon. And as you can see, the model itself made good points as to why you should own your LLM locally and you should own your data. Now, I do understand that this process going via Jupyter Notebook was pretty tedious and it was a lot. So I've also developed another application where all you have to do is input your query and maybe your persona if you want to within a command line argument, and it'll run the exact same thing. This will be open source. This will be on our repo. So please take it, integrate it into your products, integrate it into your own laptop, and go from there. Build something cool and let us know. So now I have the kernel shut down. We're out of Jupyter Notebook. Now what we're able to do is run this main.py, input your query. I've also added personas to this. So we've been focusing on cybersecurity, but with these personas, you can do whatever you want. Let's change the context length. You can also adjust the temperature and the verbosity as well. And in these are basically just warnings that's saying that some of the nodes don't need to be ran on our NPU. Some of the nodes are better off running on a CPU. So our driver automatically delegates what node goes where. And you can see we're out of the notebook and this thing is going way faster than it was in the notebook because we don't have that overhead. And like I said, this is an open source application. You can take this, integrate this wherever you want, and own your LLM. So that's about it for the sample app. As you see, we can run it from command line. This will be on our repo. I encourage anybody to clone it, use it, integrate it into your products, use it for personal use, own your LLM, own your data. Thank you.